Coil pitch, also called coil span. In plain terms, it's simply how wide a coil is, how far it stretches around the stator before coming back. You can measure it two ways, in slots or in electrical degrees, and both describe the same physical thing. Here's the part that surprises people the first time they hear it. Coils are very often wound deliberately short of the ideal span. That's called cording, and I want to be clear up front, it is not a mistake or a manufacturing shortcut. It's a genuine, deliberate design choice with real trade-offs on both sides. By the end of this video, you'll understand exactly why an engineer would choose to underwind a coil on purpose. Let's get concrete about how coil span is actually described. If a coil starts in slot K and ends in slot K plus 2, its span is simply 2 slots. That's it. Nothing more exotic than counting. Now, what should that span actually be? The general rule is to aim the coil span as close to 180 electrical degrees as possible without exceeding it. That's called full pitch, and it's the reference point every other design gets compared against. The reason 180 electrical degrees matters so much is simple. It maximizes the flux linked to the coil, and therefore maximizes the back EMF that coil induces. A chorded or short-pitched coil deliberately spans less than that full pitch value, typically by just one slot. So, how do you actually calculate the nominal full pitch span for a real motor? There's a clean formula for it. S equals the maximum of the integer portion of slots divided by poles, or 1. In words, take your slot count, divide by your magnet pole count, round down to a whole number, and that's your nominal span in slots. Let's make that concrete. Take a 12-slot, 4-pole motor. 12 divided by 4 is exactly 3, so the nominal full pitch span is 3 slots. That's the number every cording decision for this particular motor gets measured against. There's one important exception worth knowing. In outer rotor motors, where the slot count is sometimes smaller than the pole count, the slot pitch itself can exceed 180 electrical degrees. When that happens, the coil span is simply set to its practical minimum of 1 slot. Here's the real question. If full pitch maximizes back EMF, why would any engineer deliberately give some of that up? Because cording buys you something genuinely valuable in return. A shorter coil span means shorter end turns, the loops of copper that stick out beyond the slots on either end of the stator. Less end turn length means less copper, which means lower winding resistance and lower material cost. That's a real tangible engineering win. But there's a cost too. Cording introduces flat, zero flux linkage segments into the back EMF waveform, changing its harmonic content and slightly reducing its overall amplitude. And here's a connection worth remembering. This is part of the exact same mechanism behind the trapezoidal back EMF shape we covered back in episode 2. Cording isn't free, but for most practical designs, 1 slot of cording is a small price for a real reduction in copper and resistance. Let's bring this together. First, treat full pitch as your reference, not necessarily your goal. It's the ceiling on flux linkage and back EMF, and every design conversation should start by identifying where that ceiling actually is. Second, remember that cording is a trade, not a downgrade. Shorter end turns and lower resistance are real wins, and the back EMF and harmonic cost that comes with them is usually a small, acceptable price. And finally, keep the connections in mind. The zero flux linkage segments cording introduces tie directly back to the trapezoidal back EMF shape from episode 2, and coil span itself is one of the core winding assumptions behind valid pole and slot combinations, which is exactly where we're headed next.